So now let's talk about speeding up the search with the use of simulations and statistics. So we looked at the time complexity of alpha-beta pruning with heuristics, where we apply a cutoff at some depth d. With some perfect ordering, this will be OB to the power of d divided by 2. We've said that for some games like Go, it'll have a large branching factor, like around 361. This is still too many nodes to explore. Even if you apply that cutoff, you'll be 361 divided by 2. That's still too large exponentially. And for some games, it could also be difficult to define a good heuristic. So what can we do in this situation? There's a method called Monte Carlo tree search, or MCTS for short. It's a suitable strategy or algorithm that you can apply for games like Go if your branching factor is large, or when you feel that a good heuristic is difficult to define. Instead of using heuristics, the MCTS algorithm, what it will do is that the value of a game state is going to be estimated as the average utility or reward over a number of simulations starting from that game state. So in other words, if in my game tree I have a state S, I'm going to compute its utility or reward or its estimate of how good this state is as an estimate of the average wins I will get from this state. And one way to calculate the average wins at this state, so let's call it the average wins, AW. One way to calculate this is that what you'll do is that you'll take the current game state, right? If it was chess, it'll be some configuration of the board. And then you will play randomly from this given game state until you reach a terminal node. And by randomly, we mean that, if the turn here is for the max player, right? The max player, you will take a random action at this state, right? So it'll go down some branch. Now the game is at this state here. Let's call it S dash. Then it'll be min's turn. You take a random action for min, and then a random action for max, and then a random action for min, and so on, right? So we call this a simulation or a random playout simulation. So once you do this, right, you play the game up to some terminal state. Here you'll know the reward, right? One of the rewards for this random path, right? So then this is one statistic that tells you that from this game state, one of the paths from this game state will lead to a win. You do this again, you'll get another reward. You do this again, you'll get another reward. You do this again, you'll get another reward, right? These are all statistics of, different paths from this current state. Once you do this enough, what you're going to do is you're going to say, what is my average of all the sum of all the rewards I'm getting down this state divided by the total number of simulations that I have played, right? So here I have 4 simulation. It'll be the sum of the 4 rewards divided by 4. So what I'm going to do is that instead of using heuristics, I'm going to estimate the value of how good a state is using the average utility or reward over a number of simulations. The more simulations I do from a given game state, the more accurate the statistic is going to be of how good that game state is. In the extreme case, if I'm at a state, what I'm going to do is explore the entire subtree under from that state. That's basically exploring all possible paths, right, from that state to a terminal state, and then you would get the exact, let's say, average utility from this state, right? You just average the rewards at this level. So a simulation, as I mentioned right here, sometimes called a rollout or a playout, is a computational playout, right? You make a computational simulation from a state and you make random moves at each turn of the game. Starting from some current state, the simulation will take player turns until the game terminates. This requires a playout policy that determines how the players in the simulation will act. What we've just talked about right now with the illustration that I gave is a random playout policy. This can work. So starting from the game of the current state, simulate computationally the turns of the 2 players until the end game state is reached. Take actions uniformly at random, right? So you perform random actions. This can work for most games, but it can be inefficient in terms of gathering good statistics with a few playouts. There are other options for simulation playouts, or with a policy that you will use to take the actions that will be taken by the two players using ideas from reinforcement learning. This is an advanced topic. This is related to the efficiency of gathering good statistics. I just wanted to keep this comment here just for the completeness of information. And for those interested, they can go search it up. But for our use case for this course, we will just assume that to perform a simulation from a game state, we will just play using random playout. So what can we do to use simulations in order to select actions, right? There's a couple of selection policies you can use. The first I want to talk about is this is motivational examples. We're going to reach what MCTS does, but the first simple one is the following. Something called an equal or uniform selection policy. Consider that you're given a budget of n simulations, okay? What you're going to do with that budget is you will equally distribute these simulations to each child from a given node, and then record the fractions or the average number of wins. This is called an equal selective policy because it assigns your budget simulations to each child. So the way it would work is as follows. Imagine Max, inspects the game board, and then he wants to decide what action he should take. What he's going to do with this equal selection policy is as follows, right? He'll start the root node. This will be the max node. And he has a budget of n simulations. And let's say he has three actions, A1, A2, and A3. What he's going to do is that he's going to, give n over 3 simulations to the right child, n over 3 simulations to the middle child, and n over 3 simulations to the left child. So he equally distributes the budget. Then at this state, right, he will update the state from action A1. At this state, he will play n over 3 simulation. So what I've seen here is that he had a budget of 300, right? He had a budget of 300, and then he gave 100 simulation budget to each of its children. So at this state, you play 100 random simulations. At this state, you play 100 random simulations. And at this state, you play 100 random simulations, right? And when you play these random simulations, you will get wins or losses for the max player, right? And you record this, right? So for this game state here, this is the statistic for the win rate for the max player. For this state here, this is the statistics for the win rate for the max player. And from this state, this is the statistics for the win rate for the max player. And this is not exhaustive. This subtree here could be very massive. The idea is that you don't want to perform too many, maybe you have a budget, a time limit where you can't perform too many simulations. So what you're going to do is that you're going to perform an equal selection policy. If you had a budget of 300, just, give 100 to each child and then play those simulations and then just use the statistics that you have. Of course, the higher the budget is, the better that statistic will be. Right? From statistics, you guys know this. If you want a good estimate of the mean, you want more samples from the distribution. So given these statistics, so these are the current statistics that you have, what you can do is which action is the best? Should it be A1, A2, or A3? I'm going to select the action that is going to lead me to higher win rates, right? So I'm going to pick this right branch. Another selection policy that's a bit better in terms of efficiency is something called exploitive and explorative selection policy. What we're going to do is that, if I'm given a budget, I'm going to allocate some of that budget to uncertain nodes. This is called exploration. I'll talk about what we mean by uncertain. I'm going to allocate some simulation to promising nodes. This is called exploitation. And the way it would work is as follows. Imagine you had a budget of n at this root node here, and you want to know, how many simulations should I give to each of my children? Well, what you can do is that in the beginning, you don't know which of these states are actually the best. So what you'll do is that you'll maybe do 5 iterations, some fixed number for each of the children. So do 5 simulations at each child, get some statistics. So these are 5 samples for each of these children. Then after getting some statistics, what you're going to do is that you're going to allocate more budget to the nodes that have a higher win rate. So for example, if I did 5 statistics and I found that maybe this is 1 over 5, I found out that maybe this is 2 over 5 win rate, and maybe this is, I don't know, let's say, maybe let's change this. Let's say this is 4 over 5, this is 2 over 5, and let's say this is 1 over 5. right? If you had this scenario here with this, so the first scenario of just allocating some exploration budget is called exploration, right? To find out some information about the statistics of the children. At this point, if you still have budget, what you can do is that you can allocate simulations to the promising nodes. So from the statistics that we currently have, 1 over 5, 2 over 5, and 4 over 5, this looks to be the most promising because it has the highest win rate. So I'm going to allocate more simulations to this node. Okay. And as I allocate more simulations to the node, I'm going to gather more accurate statistics for this node. And the more accurate statistics or the more simulations you'd give, the more certain you're going to become of the statistic, right? Now, this node here becomes less certain, mainly because you didn't do a lot of samples. So maybe then you allocate some budget here. So with this policy, the idea is that you have a total budget, but you're going to, selectively give some budget here for exploration, then maybe some budget here for exploration, then maybe some budget here for exploration, then allocate maybe some for exploitation, maybe some for exploitation, maybe some for exploration, and so on. You keep doing this to allocate budget here and there until you exhaust your complete N. Right, so it's not very clear, but this is one policy you can apply, and for us to make it really, automated, here's what MCTS does. MCTS will use something called UCB1 selection policy. The name UCB comes from upper confidence bound. For those interested, this comes from a famous problem in reinforcement learning called multi-armed bandits. You can read on it. So what does UCB do? Specifically, MCTS uses UCB1 formula to rank the game tree nodes. So if I'm at a node here and I have children, I want to know which of the children should I allocate budget. UCB1 is one way where you can compute the UCB1, formula for child 1, UCB1 formula for child 2, and UCB1 formula for child 3, and it will give you a value, and the one that has the highest UCB1 value, you will allocate a simulation to. Okay, and it combines both promising and uncertain. What does it look like? UCB1 takes a game node. There are two terms in this formula. There's this called exploitation term. Then there's a trade-off value. This is something you need to set. There are some theoretical arguments that this should be the square root of 2. For our purposes, we'll always just set this to 1 just for learning purposes. So the first term is called exploitation. What is this computing? UN here is the total utility or reward of the simulations for node N. In other words, this is the number of wins. Okay, so the number of wins is from the game state. So I have my game state here, right? I'm going to calculate the number of, I'm going to do simulations. So UN is going to be the number of wins I get from those simulations. N here is the number of simulations I did, okay, at this game state here. So what is this term computing? This is just computing the average win rate for the given game state. Now this term here is interesting. What this is computing, this is actually computing the exploration term. How uncertain am I for this particular game node here or game state here? I'm going to be uncertain if I did not do a lot of simulations at this node. If I didn't do a lot of simulations, this exploration term will be very high, right? So the second term here with the square root is large when n, so if you look at this, this is taking the logarithm of the number of simulations at my parent divided by the number of simulations at the child. The number of simulations at a parent is just going to be the number of simulations of all the children. So you sum all the simulations at the children. If the number of simulations at the parent divided by the number of simulations at a given game node, if the number of simulations at a parent is, let's say, 100, and one of the children only has 5, that means a lot of the other children, maybe this had 5, maybe this had 90, or maybe 60, and this had 35, right? So the number of simulation at the parent will be 100. So for this particular game state here, what is this term here? This term will be large. Why? Because it's going to be the logarithm of 100 divided by 5. What about for this game state here? It'll be less than ln 100 over 5. It'll be ln 100 over 60, right? So the idea is that if you don't have a lot of simulations, this term will be very large. So what we're trying to do is that we're trying to compute a value for the game state that is some combination of the win rate at the game state and how uncertain am I of the statistics. Remember, this is the statistic for the win rate, but I also want to know how certain am I of this statistics. I am certain of this statistics if I have a high number of simulations from that node. So this gives you an automatic way to merge both the exploitation term and the exploration term. This will be your selection policy for which of the children to allocate a budget simulation to. So let's look at a particular example. Imagine this is my current game tree. This is my root node. These are the children of the root node. This is the max player turn. This is the min player turn. These are three actions, A1, A2, and let's say A3. These are the current simulations I've done so far. At each of the children, I've done 100 simulations here, 10 simulations here, and 100 simulation here. So in total, the parent has 200 simulations from this state, right? It's a sum of all the simulations of the children. In terms of the statistics I'm gathering, one notation we will use is that for the min levels, right? This is the level or the min turn level. I'm going to show the statistics for the max player. Okay, so these are the win rates. So at min nodes, we're showing the win rates for the max player. And at max nodes, we're showing the statistics or the win rates for the min player, right? So this is important. So what is, imagine I want to do one more simulation. Which of these children should I allocate a budget to? Well, we're going to use the UCB1 selection policy. So I need to compute the UCB1 formula for child 1, child 2, and child 3. So this is what it is. The UCB1 formula for child 1 is the win rate, which is 0.61, plus the exploration term. This is going to be ln 210, ln of the parent divided by the number of simulations at this child and the square root. So you can compute this, you'll get 0.23. So the score for this state here is going to be 0.84. What about for this one? It's going to be 0.6 plus the exploration term. You can do the math. It'll be 1.33. What about this one? It'll be 0.48 plus 0.23. So 0.84, 1.33, and 0.71. This has the largest UCB1 value. So I'm going to allocate the budget to this node, perform a simulation, and then update the statistic. So at the start, MCTS has a single root node in the game tree. So this is how you apply UCB1. But at the start, MCTS this is an overview of MCTS, and I'll show a full working example. So at the start, what you're going to do is MCTS will have a single root node in the game tree for the current state of the game. In each iteration, MCTS grows the game tree by doing the following three steps. It will do a selection, meaning given the current search tree's root node, it recursively applies the UCB1 formula to choose a path down to a leaf node. So from the current root, I'm going to go down the tree until I reach a leaf node. The simulation, I'm going to run a simulation from the root node, right? So this is a simulation. I'm going to get some statistics here and back propagate this statistical result, which is the win that I simulated or the loss, back up the root. So in this way, I am growing the tree by getting more simulations and growing my tree to get better and better statistics. When the time runs out, I'm going to choose the action from the root leading to the child with the highest number of simulations. Why not choose the child with the highest average utility? Well, you can do that, but it just so happens that if you apply the UCB1 formula, the node with the most playouts have less uncertainty in their estimates. And so with the UCB1 selection policy, the child with the highest number of simulation is almost always the one with the highest average utility. It's just that the way the UCB1 formula is set up, if you do a good number of simulations from the root, you're going to end up having a situation where if you look at the number of simulations at all the children, it's just that you're going to allocate over time more simulations to the node with the highest average win rate anyways, right? And this is not always the case. We're just saying there's a high probability that this happens. So one thing I want to emphasize again is that once you run MCTS for, let's say, 10 iterations, you'll have some game tree with statistics. You just care about which action to take at the root. So you will select the child with the highest win rate. Oh, sorry, the highest number of simulations. This is just an overview. I'll show a forward working example. There's more description if you're interested about the technical details at this link. And this is used for your information in the Komodo chessbox and also in AlphaGo. So let's look at a full working example. Imagine I had a game where, I'm not going to show the game state, but let's say that the game always has two actions. Okay. I want to show you just how the game tree grows if you use MCTS. Initially, right, this is the current root node game state. You have no statistics because no simulations have been run so far. You're going to generate its children nodes, and also there's no statistics here. So you're just going to write 0 over 0. In terms of computing the UCB for game nodes or states that have just 0, 0 or no simulations, we're just going to give it a special case of saying UCB for this is going to be plus infinite. Okay. So let's say I want to apply one iteration of or one simulation. Which of these two children should I give the simulation to? The way that MCTS works is that given the current game tree, start from the root and apply UCB1 formula to the children and keep moving down towards the nodes in your tree that have higher UCB1 value until you reach a leaf node. When you reach a leaf node, you will apply a simulation and update statistics. So given this current situation, this is what you'll do. The UCB1 for both children is infinite. I'm at the current root node. I compute the UCB for the two children. It's infinite. So both of them have the same UCB max value. I'm just going to break the tie randomly, right? So let's say I pick the left child. Now at the left child, I move down the tree. I'm now here. This is a leaf node. I will apply a simulation. So I'm going to run a simulation with a random policy. And let's say that it's a win for the max player. Because it's a win for a max player, I will update this statistic, right? Remember that this is the min level. The stats shown are for the max player. So I have one win for the max player out of one simulation. And at the same time, you want to, update the parents. So when you update the parents, this is a max level. You're showing the stats for min. So far at, for this update, it'll be 0 losses or 0 wins for the min player at this level. So now I've updated all the parents. This is one iteration of applying one simulation in MCTS. Okay, and you can see that the game tree has been generated. One extra detail I want to mention is that when you play a simulation and you update the statistics for the leaf node, you want to generate the children for that leaf node in your game tree and give it 0 stats. Okay. All right. Let's apply another iteration. The same policy. You start from the root node. Starting from the root node, I'm going to compute the UCB1 formula for the two children. Right. So I'm at here. This has a higher UCB1 value, so I'm going to go down here. Now I'm at here. Is this a leaf node? Yes. Then play a simulation. Let's say it's a win for the min player. Update the statistics and add the two children at the leaf node that you simulated. This is iteration 2 has been done. So you can see the stats have been updated. Let's do another third iteration. I'm here at the root node, compute the UCB1 for the two children. This is the UCB1 value. You can see that this is a higher value. This is the UCB1 formula. You can, verify the math. I'm at this node. I'm still not a child. Compute the UCB for the two children. Break the tie. Let's say we went down this child, play a simulation. Let's say it's a win for min. Update the stats. You can see this has been updated. The children have been added. This stat has been, so update the stat for this, back propagate the stat to the parent, and then back propagate the stat to the parent up to the root node. Right? Now let's do one more iteration. Right? I'm out here, compute the UCB for both children. I will go down this left path. Now I'm here. I'm not a leaf node. Compute the UCB for both children. I will pick this one, go down. Now I'm at a leaf node. Play a simulation. It's a win for max. Update the stats for this new. First add the children. Update the stat for this node. Back propagate. Update the stat for this node, and then update the stat for the root. Right. So after iteration 4 is done, this is the current game tree. You can run more iterations if you'd like to get more and more accurate statistics. But let's say you want to stop. If you stop, well, how you're going to select the action? You have two actions. at the root, action 1, action 2, you're going to select the action that has the most simulations. It just so happens to also be the one that has the higher win rate. So I'm going to pick, this one, this action here. So I'm going to pick action 1. So that's how MCTS operates, right? And it's an effective algorithm if you have you can't generate or define good heuristics for the problem, or you cannot you have a limit, you have a large branching factor, so you have limited time. It allows you to at least do the best you can with the time limits and resources available to get as many good estimate statistics as you can. The final topic I want to talk about related to games is, so far we've looked at games that don't have an element of randomness. Okay, let's now talk about when you do have an element of randomness, which are called stochastic games. Typically, we'll just use the toy examples of games that have, a dice that you need to throw. These induces some randomness because it defines some aspects of the game that you are allowed or not allowed to do. So in such game, when you grow your search tree or your game tree, you're going to need to account for the randomness via something called chance nodes. So we're going to introduce a level or levels in this tree that are called chance levels. So in stochastic games, we have max nodes, we have min nodes, and we also have these chance nodes. For example, the game of backgammon, you don't really know how it works, but there are two players, black and white. The player whose turn it is, before he takes an action, he's actually going to throw two of these six-sided die. And then depending on the outcome of that dice, the player can make certain moves or actions. So he's limited in the number of actions he can do based on the outcome of the dice, right? So how do we incorporate these chance nodes in the game tree? Let's say you had, some element of randomness in your game. All right. And let's say, for example, it's some, binary action where the outcome is, 0 or 1. Okay. And let's say that the probability of the 0 outcome is 0.9 and the probability of the 1 outcome is 0.1. And depending on that outcome, like this could be, a flip of a coin, heads or tails. Depending on the outcome, if the outcome of 0, there's a 90% chance you'll go down, you'll have a certain, set of possible actions. Let's say action 1, action 2. Or if it's the other outcome, you have another set of actions. Let's call it B1 and B2, right? So they do define the situation that you end up in. How do you calculate the utility for this chance node? Very simply, we already know how to calculate the utility or the utility for a min node, right? If these are two terminal states and I'm at a min node, I just take the min of the children, right? So min of this and this is 2, min of this and this is 3. All right, if I'm at the chance node, how do I calculate the utility of the chance node? Very simply, it is just the probability or the weighted sum where the weighting is done by the probability, right? So look at all your children and compute the utility of the chance node as the sum of the probability of the child times the utility. So for this node here, where did we get 2.1? 2.1 is just 0.9 probability times the utility of this child, which is 2, plus 0.1 probability times the utility of the other child. This is going to give you 2.1. So it's just the, the weighted probability, the weighted sum where the weighing is done via the probability. So let's look at, a simple game. Imagine you have a simple 2-turn game. So just max takes an action and then min takes an action and the game is done. Let's say that typically the way this is applied, let's say that this game had an element of randomness consisting of a coin flip where you get heads or tails. Okay. So what's going to happen in the real world is the following. This is the current game state for some game. Max's turn, and Max wants to use searching of the game tree to select the best action. What will happen initially is that Max will perform the coin flip in the real world because he wants to remove the element of randomness, at least for the turn he's going to take right now. So he's going to do the coin flip, right? After the coin flip, he'll know the current state and he's removed for his current turn the element of randomness. This is the state of the root node, right? So before this state, there was the randomness for the max player. And this randomness has been removed because the max player has already taken that event. He's performed that event. And after that event, he will form the state at the root node. Now, after this formation, he wants to determine, what actions should he take at the root node, right? So he'll have two actions, action one and action two. Let's say it's a two action game. Now, after he takes an action, he knows what the game state will be, but then at this turn, it'll be the turn of Min. And when it's Min turn, Min has to actually perform the coin flip. So these chance nodes are for the coin flip of the Min player. And these are the two actions for the max player. So if the max player takes an action, he'll go down, a state. This is a particular state transition. Then Min will need to take his random event. This, let's say, will perform the outcome of the coin flip. This could be heads. This could be tails. This could be heads. This could be tails. This is another state. Let's say S1. This is S2, right? And then based off of the outcome of Min's coin flip, he will have, a certain set of allowable actions. All right. And this is how the game tree will be, generated. I want to emphasize that this is, the turns associated for Min. If the game tree had more moves, the next two levels after this will be the random event associated with max, and then followed by the max nodes, and so on, right? So in a game where there's stochastic element, the levels of the game tree consist of alternating levels of, min chance nodes, then the min nodes, then the max chance nodes, then the max nodes, and so on up to a terminal level, right? And the way you would compute the utilities for this level is just take the min of the children. And then for the chance nodes, it's just the, 0.5 times 2 plus 0.5 times 4. It's the same thing, 0.5 times 0 plus 0.5 times minus 2. And then at this rote, you just take the max. And which action should you select? It should be the left branch. That's how this is a simple game tree, but this is how you would do it with this mini games with elements of chance, how you would apply minimax. So now consider a game where you have dice throws. So what would the game tree look like? Suppose it's Max's turn. How do we compute the best turn? For the first, like I said, when it's Max's turn for the given game state in the real world, what he'll do is that he'll throw the dice so that he can know for certain what the outcome of his current state is going to be. He'll remove the randomness, and then he'll start to set up the first root node after the randomness have been removed, and then he'll start doing actions, and then this will be min random event followed by min nodes, and then max random event followed by max node, and so on. So for this dice throw here, there are 36 possible outcomes for two six-sided dice. Assuming the dice are paired, then the probability of each outcome is 1 over 36. For games like backgammon, this is something unique with backgammon, 5, 6, and 6, 5 both lead to the same set of legal moves. Thus, there are really 21 unique branches. So the 6 doubles 1, 1, 2, 2, 6, 6 each have a probability of 1 over 36. And then there are 15 permutations, 3, 2, and 2, 3 both lead to the same set of events or restrictions on the actions. So we'll just give this a probability of 2 over 36 or 1 over 18. The probability of all outcomes at the chance levels need to sum to 1. Okay, so this is the illustration of the game tree for backgammon where there's a dice throw. Before the start of the game, like I said, for the current state, Max has already thrown his dice, so he knows the restrictions on his actions. The root of the game tree will consist of the current state, and he knows what actions are available because he's done the dice throw. So this is action 1, action 2, all the way up to some action number k, right? So these are the actions that Max can take. And after taking an action, he will transition to, some state, all the way up to some state k. Now, these are the levels for the min player. First, min needs to throw the dice for every, state here. He needs to throw the dice. And then after throwing the dice, he will then know what actions are available. So let's say he goes down, let's explore this path here. This is some action. At this point, Max will have some state. He will throw the dice. He has these possible outcomes for the dice throw, right? 6, 6, 6, 5, blah, blah. There's probabilities associated with each dice throw. And after throwing the dice, he'll know, what actions are available, right? And so on, right? This is how the game tree is grown by Max computationally, right? There's levels of alternating chance and min nodes and so on until you reach terminal states, and then you compute the min nodes, you compute the chance nodes all the way up to the root, and then at the root, once you've computed all the utility of the chance nodes under it, you can select the best action. So this is very simple modification to min-max. So the way you would do it is we call this expect minimax because it computes the utility as the expected utility of probabilities. The only change we do is that if you're at a max node, you're just computing the max of the children nodes. If you're at a min node, you're just computing the min of the children node. But if you're at a chance node or chance level, you're computing the utility as the weighted probability, right? If you're at a terminal node, it's just going to be utility. So the only change to the minimax pseudocode is you just need to add another, function and level for the chance nodes. What is the time complexity for expect minimax, right? Let's say that the max number of turns until the game ends is OD, okay? Is it the same as minimax? In minimax, if you had a branching factor of B, then it's going to be OB to the power of D in the worst case. Well, no, it won't be. The reason is because we need to account for the chance nodes. If there are ON branches for the chance node, meaning for a given chance node, at most you will have ON outcomes for your random event, then the expected minimax is going to run in the worst case as follows. This is to account for the branching from the max and min nodes, and this is to account for the branching from the chance nodes. So in total, it'll be OB to the power of D multiplied by N to the power of D. How to speed up expect minimax? Well, we can apply all the techniques we've discussed before. So you can cut off the search at a specific depth and then apply heuristic, or you can use something where you apply Monte Carlo simulations as well to compute statistics for non-terminal game states. You can use an adapted form of alpha beta. There is an expected minimax version of it. For chance nodes, the alpha beta are bounds on the expected utility. This is also something you can explore on your own. So we won't really go, expect this to go into technical details for these two extra ways to speed up the search for expected minimax, but it's good to be aware, and definitely you can go explore it on your own. And with this, Jazakum Allah khair, we finished the topic for games. Assalamu alaikum wa rahmatullahi wa barakatuh.